Okay, we're going to continue our journey from the basics of thermodynamics to understanding chemical equilibrium. So we've gotten to the point where we understand that it's a change in entropy of the universe that determines whether a process is spontaneous. And we are going to be able to calculate that based on properties of the system, usually using a delta G. So we're going to first move from that simple understanding of thermodynamics now to understanding what happens when you create a mixture. So after you create a mixture, you'll be able to create a mixture that reacts. So first we have to think about mixtures and phase equilibrium, and then eventually we'll get to chemical equilibrium. So simple mixtures, the thermodynamics of mixtures, and we're on our way to understanding that what happens when a mixture can react. So the first thing we want to think about is a definition that's very precise. It's called a partial molar quantity. So it's easiest to visualize when we're talking about volume. So we'll look at some graphs. But a partial molar quantity is just how that quantity changes as you change the number of components of, or the number of moles of a component, holding pressure, temperature, and all other components constant. So if I say the partial molar volume of J is equal to how does the total volume change when I add an infinitesimally small quantity of J holding everything else constant. So holding the other things constant is important, and the value depends on composition. So let's look at this figure that shows us something about partial molar volumes. So this is a very good graph. The top of this page 144 shows you if you have a mixture of water and ethanol, that as you add the two, the total volume actually changes in very different ways. So this is the partial molar volume. Down here, it's how the total volume changes. So it's not just a linear function. Volume just doesn't change as you add the two components together in a positive way. So it's really based on the idea that there are different interactions depending on the relative composition. So the partial molar volume of ethanol actually goes down and then goes up. So it has a negative impact on volume, essentially because when water and ethanol interact in small quantities, they are more ordered than they are as individual systems. So these graph shows you that it's really a complex relationship, and that the composition, so as we move across mole fraction of ethanol, the partial molar volume of both the water and the ethanol are changing. So that's important to realize. So if we wanted to know the total volume change, it would be the partial molar volume of each component times how many moles of each component we added. So this is just like writing a total differential for any thermodynamic function, like we did with internal energy, Gibbs free energy in focus 3. So now, because we're going to label this derivative just to be Vj, that would mean I can replace this derivative with our symbol Vj, or Va, times the infinitesimal change in moles of A and the molar volume of B times the infinitesimal change in moles of B. So self-test 5A.1 on page 145 tells you that you have a 50% by mass mixture of ethanol and water, gives you the density of the solution, and it gives you the partial molar volume of the water. And it asks you to calculate the partial molar volume of ethanol. So you have enough information to get the total volume. You have this. We have the number of moles because we know the concentration. So if we start out and we assume that we have 100 grams of solution, then we have 109 cubic centimeters. But if we have 100 grams and it's 50% by mass of each of those components, we have 50 grams of water and 50 grams of ethanol. So you could figure out the moles of each of those. So you'd have moles of water, moles of ethanol, and the total volume, and the partial molar volume of the water. So it'd be fairly easy to calculate that. So just take a little break and finish that problem and see if you get the answer that the book gets. So we're going to be more interested in partial molar Gibbs free energy because we're going to give that a special definition because it's really a measure of the tendency for a reaction to take place. We'll see as we go on. So the partial molar Gibbs energy is defined as a chemical potential. So we'll use those two words or two names at different times. So the chemical potential of J is how does the Gibbs free energy change as you change the number of moles of J, holding the pressure, temperature, and all the other number of moles of other substances in your mixture constant. So if you have a pure substance, then it's going to be true that the total Gibbs free energy is the number of moles of J times the molar Gibbs free energy of the J component. And if the molar Gibbs free energy of the J component is the chemical potential of J by our definition, then yeah, so then we can replace each molar Gibbs free energy with the chemical potential, and we have the same equation. So the Gibbs free energy equals number of moles of A times the partial molar Gibbs free energy, number of moles of B times the partial molar Gibbs free energy for B, and each of those is by definition a chemical potential. So now if we write out the entire way that a Gibbs free energy can change, an infinitesimal change can be a function of the pressure and the temperature change. So we derived that relationship back in focus 3. But now we're going to allow the composition to change. So can also change because the chemical potential times the number of moles of A that might be created in a reaction or added from another flask times the chemical potential of B times the change in number of moles of B. So this sum could go on for as many components as you have. So this is called the fundamental equation of chemical thermodynamics, and we'll see it's our starting point for almost everything we do for the rest of our equilibrium discussion. So if we're at constant temperature and pressure, then these first two terms are 0. And it turns out that the Gibbs free energy changes as a function of changing number of moles of different components. And the proportionality constant for each of those is their chemical potential. Because this chemical potential, remember, was how does Gibbs free energy change as you change the number of moles of A. So that will be our situation anytime we're carrying out a reaction at constant temperature and pressure. The Gibbs free energy is going to change because the composition is changing. So from the last, or from focus 3, not from the last one, from focus 3, we saw that a change in Gibbs free energy at constant temperature and pressure was equal to the maximum amount of additional work, so maybe electrical work or any other kind of work besides PV work. And so that means this is equal to this, and this is also equal to this. So the maximum amount of work you can get is equal to the chemical potential of each component times the change in number of moles of each of those components. So we're going to be able to use that when we get further, and we're talking about like electrochem, where your additional work is electricity, and that's a result of changing the composition of your solution by having a reaction take place. So that's a ways off, but that'll be an important idea. The Gibbs-Duhem equation is important in the sense that it allows us to think that the chemical potentials have to change in equal and opposite ways, essentially. So the Gibbs-Duhem equation says the chemical potential, or the Gibbs free energy total from up here is equal to the moles of A times the chemical potential of A, moles of B times the chemical potential of B. But we also know from a total differential point of view that dG is going to be equal to, if we look at this guy, the chemical potential of A times how did the number of moles of A change, chemical potential of B times how did the moles of B change, but the chemical potentials themselves are a function of composition, so they'll be changing. So essentially we're taking each of these, dNA mu A is equal to NA d mu A plus mu A d NA. I think you can see that okay. So just like we expanded any differential to be hold one constant, change the other, hold the other constant, and change the one that you held constant in your first change. So we'll get 4 different terms. But if you compare this equation back up to this equation, what you'll notice is that the sum of Na times how does the chemical potential of A change plus Nb times how does the chemical potential of B change, those have to add up to 0. And so that is the Gibbs-Duhem equation, where you may have more than 2 components. So it's just a sum over all the components. When you have 2 components, what it really is telling you, it's easy to see that the chemical potentials of A and B change in relation to each other. So one goes up, the other goes down. And the proportionality constant in this case is the number of moles of each of them. So this will be an important thing to understand as we look at how chemical potentials change in reactions. We know that as one goes up, the other goes down, and the proportionality constant is the number of moles of each. So for any partial molar quantity, you could write a Gibbs-Duhem equation. So it's always going to be true that there's a relationship that the chemical potential of A and B can't change independent of each other, nor could their partial molar volumes or any other partial molar quantity. So we'll come back to this. So it's one of the reasons I wanted to do these notes and have lectures like this, so that you have these things in your notes, because we'll be coming back to ideas like this when we get to chemical equilibrium. So the thermodynamics of mixing. So now we're going to mix. We've defined the chemical potential, and we're going to use that rather than a Gibbs free energy, and see what happens when we mix things. So if we start out and mix 2 perfect gases, then the chemical potential is equal to the molar Gibbs free energy for each of those gases. And back in focus 3, we looked at the fact that the Gibbs free energy changes when pressure changes as a function of volume. And if we have a perfect gas, we derive this relationship where volume can be written as a function of P and T. And if it's constant temperature, yes, then we end up with this equation. So we derived this on the board back in focus 3. So now we're going to look at mixing 2 components. So this means we can just rewrite our Gibbs free energy. So a molar Gibbs free energy is really a chemical potential. And a molar Gibbs free energy at a standard pressure is the standard chemical potential. And the chemical potential is going to change as a function of pressure. So it's going to be exactly the same term here. But if you always work in units of your standard pressure, then you can make your equation look simpler. So if our standard pressure is 1 bar and I work in those units, then this is dividing by 1, so I can leave it off. That gets a little confusing, but always remember that each and every one of your pressures is always divided by the standard state. So it ends up unitless, which will be another important thing to think about, but it's going to make it easier. I mean, if I worked in millimeters of mercury, I couldn't do that, because then my standard pressure wouldn't be 1. So the first thing we're going to do is we're going to mix 2 gases. They each start at a pressure P and they end up at a pressure P. So this will look like page 147. Yeah. So we have 2 containers. Both gases have the same pressure. We have a different number of moles of A and number of moles of B. But when we mix them, we essentially just take out the barrier, and their total pressure is going to be equal to their individual pressures when we started. So we're going to write the chemical potential for each of those pure substances first. So initially we have them separated by a barrier. So we'd have the chemical potential of A times the number of moles of A, plus the chemical potential of pure B times the moles of B. And so if I write that in terms of how chemical potential relates to pressure, I'm going to put this in for each of my gases. So the chemical potential of A is going to be the chemical potential of A if it was at 1 bar, plus RT times natural log of whatever pressure we're at. Same thing for B, chemical potential of B if it was at 1 bar, plus RT ln of whatever pressure we're at. After we've mixed them, then the final Gibbs free energy is going to be the number of moles of A times its new chemical potential, and its new chemical potential is a function of its partial pressure. So when the total pressure is the same as you started, each individual gas has a partial pressure that's going to be lower. So partial pressure of A, and then over here, same thing, it's going to be the partial pressure of B. So after you've mixed, you've gone from each gas, it's probably easier to look at that picture, each gas having the same total pressure to down here, if the system has that total pressure, the component that has the more moles will have the higher pressure, and each of their partial pressures will be added up to get that total pressure. So now if I take the difference between the mixture and the pure gases separated by a barrier, just take the difference in this and that, then you'll see first that Na times chemical potential of A at 1 bar, Na times the chemical potential of A at 1 bar, those two are going to cancel if I take this minus this, and we end up with Na times chemical potential, so times RT ln of PA minus RT ln of where it started at P. Same thing will be true for B. The chemical potential at 1 bar is going to cancel this term minus this term, but then the second term will be RT ln of partial pressure of B in the mixture minus where it started, RT ln of the pressure total. So I can just group these. Ln of X minus Ln of Y is equal to Ln of X over Y. So now we have number of moles of A, RT ln of PA over P, plus NB RT ln of PB over B, RP. Then we want to think about the relationship between partial pressure and mole fraction. So the mole fraction times the total pressure equals the partial pressure. Therefore, I can replace partial pressure of A over the pressure total is going to be the mole fraction of A. And then when we look at the mole fraction is going to be number of moles of A over total moles of A and B together. Therefore, if I just rearrange this, moles of A is going to be equal to N, the total moles, times the mole fraction. So I can just put in those now. So I can say partial pressure of B over P is equal to the mole fraction of B. Partial pressure of A over total pressure is equal to the mole fraction of A. And if I want to get rid of the moles of A and the moles of B, the total moles times the mole fraction of A is equal to the moles of A. And same thing for B. So that allows me to pull the total number of moles out front and have this just a function of mole fraction. And so Gibbs free energy changes upon mixing two perfect gases. Will it always be spontaneous? And so when you look at this, the mole fractions are always less than 1. So ln of something less than 1 is going to be negative. So this will always be negative. So by putting mole fractions in instead of pressures, it's easier to see kind of the general physics of that equation. When you mix two perfect gases, it's going to give you a negative delta G for mixing. So self-test 5.8.3 on page 149. I want you to stop and do that one. In order to do it, it's very similar to the problem above it, so you can watch how they went through the process, but notice it's a different problem in that initially these two gases aren't at the same pressure, and then the final pressure is not the same. So that means that you're going to have to derive a different initial and different final situation to get a delta G of mixing when the gases don't start at the same pressure and don't end at the same pressure. So stop first and derive that. So read the problem and it'll help just do what we did here. write your G final and your G initial in terms of what the pressures are, and you'll be able to derive an expression that's similar to the one at the bottom, but not quite as simple. So stop and do that. So for other thermodynamics of mixing, we know that S is equal to dg dt constant P. So if I want to know what the delta S of mixing is, the delta S of mixing is going to just be delta G of mixing, take the derivative of that with respect to T. When you look at our equation, you will see that that's an easy derivative to take. It's just a bunch of stuff times T. So if you're taking the derivative of this with respect to T, you get NR, all of this stuff in parentheses. And so when you look at that, because there's a negative out front, that means that if delta G of mixing is negative, delta S of mixing is always positive. And that will tell us that the process is spontaneous only because there's no heat transferred with the surroundings, because delta H of mixing for perfect gases is 0 because their interactions don't change at constant T and P. Therefore, you're not exchanging heat with the surroundings, so the only entropy that's changing is the gas mixture. And so this having a positive delta S of mixing means it's just confirmation that, yes, it will always be a spontaneous process for two gases to mix. So we need to be able to go from gases to liquids, and that will be the last thing we do in this topic A. What is the chemical potential for a liquid? So the very, very, very important thing to think about is this right here, that the chemical potential of any liquid is always going to be the same as the chemical potential of the gas that's in equilibrium with it. If that wasn't true, you'd have some gas move back to the liquid phase or some liquid move to the gas phase. So they're in equilibrium with each other when their chemical potentials are the same, because otherwise a change in chemical potential would result in lowering Gibbs free energy, and you would have that movement. So the chemical potential of a pure liquid, so the star means pure liquid. So if we're talking about A, its chemical potential is going to be equal to its chemical potential in the gas phase. The chemical potential in the gas phase will be the chemical potential of A if it was at 1 bar, plus the chemical potential change as a result of, you're going to be at the, gosh, I can't think of the word for that. Just the vapor pressure of the pure liquid. So what is the pressure above a pure liquid? It's not going to be 1 bar, it's going to be something else. So this basically is the vapor pressure of A when it's pure. So the vapor pressure of the liquid when it's pure is going to be equal to the chemical potential of A for the standard state. And technically this is divided by 1 bar, but like we said earlier, you can leave that out. But this, I think I'll put it in to remind you that you're really changing the chemical potential to what it is when you have a pure liquid and its pressure is equal to the vapor pressure rather than 1 bar. So if the liquid is in equilibrium, that's going to be true, and that's going to be a super important thing as we move from perfect gases to liquids where we don't really have good equations of state. So the chemical potential of the liquid is equal to the chemical potential of the gas plus RT ln of whatever partial pressure you have for the gas. So this is saying if you're in a mixture and you don't have pure A, then it's going to have a partial pressure different than the vapor pressure of the pure substance. So if you're in a mixture, A is not pure, your chemical potential is still equal to the chemical potential of the gas, but now the gas has a different pressure. It doesn't have the vapor pressure of a pure liquid. It has a lower vapor pressure. We'll see in a second. So we're just going to rearrange it. So we're going to get rid of the chemical potential in the standard state. And we are going to do that by looking at the first equation and just moving this term to that side. So if we do that, the chemical potential of A in the standard state, So just move this to that side. The chemical potential of A at 1 bar is equal to the chemical potential of A if it was pure, minus RT ln of PA standard state. So we've just rearranged that first equation. And then if we look at the next equation, that allows us to take this term and replace it with these two terms. So the chemical potential of A when it's in a mixture is equal to chemical potential of A if it was pure, minus RT ln of PA for the vapor pressure of A, plus how much does it change because we no longer have pure A, we're in a mixture. So that's going to be equal to the chemical potential of A in its pure state, plus RT, what is the partial pressure of A compared to what it would be if it was just A and it wasn't a mixture. So Raoult's law says that for an ideal solution, the vapor pressure of A above a solution is going to be related to the vapor pressure of pure A and the proportionality constants, its mole fraction. So that allows us to look at this and say the chemical potential of A when it's in a solution, or a mixture, I'll call it, is going to be equal to the chemical potential of A if it was pure, plus RT ln of the mole fraction, because the mole fraction is equal to the vapor pressure you're at divided by the vapor pressure of the pure liquid. So let's just think about this idea of an ideal solution. Yeah, so what Raoult's law is really saying is that it's linear. So if you have methylbenzene, when you have 0 methylbenzene, it creates 0 pressure. When you have pure methylbenzene over on this axis, it's at its vapor pressure, but it's just going to change in a linear fashion as a function of its mole fraction. Goes down as it gets less concentrated. And the same thing's happening as benzene. As it's pure over here, it's at its vapor pressure, but then it just goes down as a function of its mole fraction. When you add those two together, you get the total pressure. So that's an ideal solution. And then for non-ideal solutions, you can have positive or negative deviations. So an ideal solution by definition is similar to an ideal or a perfect gas approximation, but not quite. So if you have it on our notes, if you have a solution or two liquids, so you have a solution or a sample of A and a sample of B, and then you mix them together, what an ideal solution is assuming is that AA interactions and BB interactions are equal to AB interactions. So AA interactions are equal to BB are equal to AB. So you don't have 0 interactions in the solution when it's ideal, but the interactions are the same as they would be. So if you have things that are super similar, they're going to form ideal solutions. If not, you can get either positive or negative deviations. So if you look on page 152, the gray lines are showing you what Raoult's law would show you, that it's a linear change. But experimentally, carbon disulfide has a higher pressure than would be approximated with Raoult's law, and so does acetone. So overall, the total pressure is higher. And that's a solution that has more repulsive terms with each other than they did together. So that means carbon disulfide and acetone have less favorable interactions. And so essentially you can think of it as they both want to get out of the liquid phase more, because as they interact with each other, it's not as favorable as it was when they were just pure. You could also have negative deviations where these curves from experiment were below Raoult's law. And that would mean that they interact more with each other than they interacted when they were alone, and that they're actually liking to be in solution more because the interactions are more favorable. So if you have a very high concentration of one component, it's going to behave more ideally. So when you look at this particular graph, it shows you that when you're over here where a mole fraction of B is 1, then as you look at the ideal behavior of the solution of the expected line, if it was an ideal solution and it followed Rayout's law compared to experiment, when the solution is pretty much pure B, it's going to follow Rayout's law. When you get over on the other side where B is in a very small concentration, then it's going to deviate a lot from Rayout's law because each B molecule is pretty much surrounded by A. And so the interactions have changed a lot from over here where it's B-B interactions. And so it'll be linear, but the proportionality constant won't be any longer the vapor pressure of pure B. So that's called an ideal dilute solution. And for ideal dilute solutions, rather than this being PB star, like it would be if you're talking about an ideal solution in general, instead you have to measure this experimentally, and it's called Henry's law. So the pressure of B is proportional to the mole fraction, but the proportionality constant is an experimentally measured number that's called Henry's law constant. In general, mole fraction is proportional to molality, and so Henry's law is usually written in units of molality, and then you incorporate that proportionality constant into the KB. So it's a KB for mole fraction units. So you'll probably see it written this way instead of mole fraction, knowing that it still is the same exact equation. You just have a different number for KB, which incorporates the conversion between those two. Which reminds me, one other thing I wanted you to look at. Yeah, on page 148, the Chemist Toolkit 11, just look at that and read through. They use or they tell you the relationships between the units they're going to use. So mole fraction, molality, and molarity. So just read through those and realize that they use different labels. Molarity is little c, molality is B. So just be aware that they'll have different symbols than you did in Chem 108, but the concentration units are the same. And that is all for topic 1B, or 5B. B, it's A. 5A, sorry.